spectroscopy basics we are going to learn here. And what we are going to learn today is the basic concepts of the fluorescence, and where we will try to review the light absorption fundamentals and also look at the excited state processes, photophysical processes, and also try to review the history of the fluorescence and fluorescent parameters. So what are the parameters that we are going to discuss? Includes the emission spectrum, excitation spectrum, quantum field, fluorescent lifetime, and the fluorescence anisotropy. These are the parameters we are going to discuss. And as we go into this session, we also should ask a question: what is fluorescence? Now, when you say the fluorescence, this was observed in the year of 1845 by Herschel, and he used the sunlight, put a glass filters, and used the quinine solution as a sample, and used another wine glass as a filter, and viewed through the bare eye. This was the basic observation of fluorescence. And later on, the name was given as a fluorescence by Einstein, which is the important nomenclature in the year of 1853. By looking at this view graph, you can really guess what is basically a fluorescence. And fluorescence is nothing but your light emission by an atom or a molecule after the finite duration subsequent to the absorption of photon. This is the basis. This is how you define the fluorescence. Now, when you look at the fluorescence, what is required is the light. When you give light to the molecule, what really happens in the molecule? It is the promotion of the electron to the excited state. Now, when you see the promotion of electron, when you consider organic molecules, you have a different types of the electronic transitions. If you see the left side picture, you have the sigma to sigma star transition, pi to pi star transition, n to pi star transitions. And the same thing can also be represented as your Morse potential energy surface. You have a ground state electronic surface, excited state surface. Electron goes from the zero vibrational level to the higher energy, electronic energy level. So we just going to follow the Frank-Condon's law, and we are going to discuss all that basics. Now you have an excitation of electron from the ground state to the excited state. If you take, for example, coordination compound, the same electronic transition won't be there. The nomenclature of the electronic transitions are different when you compare the organic compounds. The kind of electronic transitions possible when you take the coordination compound is a ligand-centered transition, metal-centered transition, and charge transfer transitions like a metal to ligand charge transfer or ligand to metal charge transfer. This is how you have the different electronic transitions possible if you go for the coordination compounds. So now absorption of photon puts the molecule in the higher energy state. This is what is called as a excitation of the molecule. And once this excitation happens, so we also should know some of the basics of the absorption phenomenon. Let us try to review it as we learn. And as I already mentioned about it, the basic law is a Planck's law. E is equal to h nu. H is your Planck's constant, which has a value of 6.63 to the power of minus 34 joule second, which you can represent the nu in terms of frequency. The term h nu is basically represented as photon. In most of the photophysicists and photochemists use it. Otherwise, in generally, it is your energy of the photon. Photons are nothing but the wave packets that you give it to the molecule. They absorb the wave packets and go to the excited state. And now, when you look at this, E is equal to h nu, you can also substitute it for frequency as a c by lambda. So this really demonstrates some of the relationship, how exactly the photon is related to the wavelength. It is inversely proportional to the wavelength, and otherwise nu is directly proportional to the energy. This is very important. And as you go for a longer wavelength, the lower energy, shorter wavelength, higher energy. This is a relationship. You always get it when you look at the Planck's relationship, Planck's law. Now, the units commonly used for the energy, joules, kilojoules, You can also use the electron volt. You can also represent in terms of frequency, which is in the units of the hertz. Now you can use these energy units. You can also use the wavelength in terms in the units of nanometer. We also have we can also relate nanometer to the angstrom. You know, angstrom is the olden unit. SI units are nanometer. So you should have all these relationship. How do we connect this with the wavelength? All that you should understand. Energy is important here. Energy units are important here, and also the wavelength connected with the color of the light that we are using it. Violet has more energy, red has the lowest energy, ultraviolet is having more energy than the visible light. This is how you see that the different photons, different wavelength of the light, energy, color that you get. You should have some basics of understanding of the photon that we use it. Now, the basic law that governs absorption is also important, called the Beer-Lambert law. Beer-Lambert law is connected to the intensity, which is the experimental parameter, which can also be connected to the molecular parameter. You see that absorbance is equivalent to epsilon CL, and one can measure the absorbance using the spectrophotometer. It can be a single beam or a double beam. For a visible region, you are using a tungsten lamp, and for ultraviolet, you can use the deuterium source. So monochromatize it, give it to the sample, measure the intensity of the transmitted light, and make a calculation of absorption. This is how the basic absorption law, which talks about your absorption behavior of the molecule, which is important requirement for the fluorescence. Before start doing your fluorescence, you need to know the absorption molecule. Now go into a little more basics of your absorption, which is your Born-Oppenheimer approximation. The total electronic energy, total energy of the system is equivalent to the sum of all the energies like electronic, vibrational, and rotational. Otherwise, electronic energy is inclusive of vibrational, rotational. You can see this in the force potential and in surface, your vibration level. So it is important approximation, which also connects with your laws of the emission also. Now when you look at the other important basics is the Frank-Condon. Electronic transitions are following your Frank-Condon principle. Otherwise, they straight away go from the ground state to the excited state. Otherwise, they go to higher vibrational state that is called the Frank-Condon state. Generally, the ground state population is in the 0-0 vibrational state, and following your Boltzmann distribution law, most of the population is always in the 0-0 vibrational. When you give an excitation, not necessarily should go to the 0 vibrational state or the excited state. It can vertically climb. It's called the vertical transition. This is something like climbing the multiple floors using a lift. That is how you can see that the vertical transition happens, and this is very important. It can be represented in the form of the Morse energy surface. You can find out how exactly the vertical transition happens. It all depends on the nature of the molecule. You may also have possibility of a 0-0 depending upon the geometry of the molecule. You can have the higher vibrational states also. Now you can also, that will reflect on your absorption spectrum. Actually, you can see the vibrational states, they are changing their position depending upon their absorption state, that is vibrational state that is associated in the electronic transition. So your electronic transitions are following a Frank-Condon rule. Otherwise, the electronic transition happening to a Frank-Condon state. Now, once you have the electronic transitions happening, and you always follow this in the form of a representation of the spectrum, which is basically called as an absorption spectrum. What is basically an absorption spectrum? It's a plot of absorbance versus wavelength. So most of us know about it, but I'm just for the continuity and for the completion, I'm trying to review the basics of absorption spectrum, and slowly we go on to the fluorescence. Now, how do we record this using a spectrophotometer? You have to scan your monochromator, take a white light from the light that you take it, and then you try to look at the absorbance, intensity of transmitted light. You have a cuvette, and light is passing What we measure is the intensity of the transmitted light. This is how you measure, record, and absorption spectrum. Now, when you go for the little more basics, and what is important is the Boltzmann law is also important. As I told you, the population in the vibrational states have the vibrational states are under Boltzmann equilibrium, whereas the electronic states are not. Now, within the electronic surface, your vibrational state population depends on the temperature. At absolute T, you can see most of the molecules are residing in the vibrational zero state, in the ground state. That's the reason why electronic transitions happen from the ground zero vibrational state to the upper states, upper electronic states. And this is important law when you talk about the absorption, which is picturized here. Zero vibrational state to the upper stage electronic transitions. So this is Boltzmann law is also important. As you see the Planck's law, you need to understand Planck's law, you need to understand Born-Oppenheimer approximation, you need to know the clarity of the Frank-Condon state and how exactly electronic transitions happen. Now, when you talk about electronic spectroscopy, there are certain selection rules coming into the mind. The most fundamental selection rule is the spin forbidden transitions. That means the electronic transitions always takes place between the spin state, same spin state, singlet to singlet and triplet to triplet, whereas the singlet to triplet, triplet to singlets are forbidden. And even if it happens, they're all weakly. You know, there is always a spin orbital coupling possible that will make the electronic transitions appear weak also. And now you also have selection rules. They also coming the now the other one is the now this spin forbidden transitions. It is possible in the case of the intersystem crossing. This is happening because of the spin orbital coupling. You should also understand that. Now, the second selection rule is symmetry forbidden transition. You can see that the symmetry plays a role in the electronic transition. So you can see that the same symmetry also sometimes happen. There is a departure selection rule is also possible when there is a vibrational coupling with the electronic motion. This is how called as a vibronic coupling. That will how really reflect. They all reflect. All the selection rules reflect in the intensity of the absorption that you see. So when you look at the absorption, you need to understand selection rule. Laws and selection rules are very important. Now let us now come back to this. Our absorption of photon, we are putting the molecule in the excited state. So what really happens when the molecule goes to excited state? There is a physical deactivation possible. There are a number of physical deactivations one can study about it. It can be intramolecular or intermolecular, and this should be intermolecular. And now you can see that you have possibility of the radiative transitions, fluorescence, and then you can see the delayed fluorescence, phosphorescence, radiation-less transitions, like internal conversion, intersystem crossing. Now you can see the other process like energy transfer, electron transfer, and vibrational relaxation. There is also possible between the two different molecular systems. So now you can see that these are all the physical processes. Now you can picturize the holistically the entire processes that would happen subsequent to the absorption of photon, and that these are basically inclusive of physical and the chemical processes that would happen from the excited state. And the fluorescence emission, intersystem crossing, as you go from left to right, you can see it internal conversion, intramolecular charge transfer, conformational changes, electron transfer, proton transfer, energy transfer, excimer formation, exciplex, and photochemical transformation. This is how you can see it. You have the possibility of different deactivation pathways of the excited state molecule. Intersystem crossing includes phosphorescence and delayed fluorescence. This is how you can look at the overall deactivation of the excited state, which can be picturized. Photophysical process can also be picturized by Jablonski diagram, which is one picture giving you all the information about the absorption. When you carefully look at this picture, which absorption, that is the first event which happens in the time scales of 10 to the power of -15 second, which is called as the femtosecond. And once you are exciting the molecule, when I say excitation, which follows all the absorption rule that we discussed so far, it goes to a Frank condensate. Vertical transition is happening. It is happening in the time scales of 10 to the power of -15. Then you have an internal conversion, relaxation within the electronic state of the same spin multiplicity. They all happen almost like a 10 to the power of less than a picosecond. You can see it almost in the picosecond time scale. From this S1, when it S1, and then it relaxes to vibrational state 0 of the S1 state, and then from S0 state it relaxes to the ground state to the other energy levels like a triplet state. You can see it, and fluorescence is happening it from 0 0 vibrational state to the ground state, and this is possible with normally happens in the time scales of few nanoseconds or sometimes sub nanoseconds. An intersystem crossing between the S1 to the T1 state, and this is your intersystem crossing, and which is happening in the time scale little faster than the fluorescence. You can see it because of the vibronic coupling. It happens faster. Excited state relaxation from the triplet state to the ground state. It can be intersystem crossing, it can be radiative, or it can be non-radiative. If it is radiative, you call them as a phosphorescence. So you have a possibility of a non-radiative. So this picture clearly tells you about what are the possible relaxations, the photophysical relaxations. The photochemical is also possible, and you have photochemical reactions, but Jablonski predicts or clearly represents the photophysical process that will happen from the excited state. So it includes radiative and non-radiative, right? This is a whole picture of the entire photophysical processes that would occur from the excited state molecule. Now this diagram was little modified by Perrin, and then it is named as a PERRIN-JABLONSKI diagram, which gives you the position of the absorption spectrum in terms of energies. Also, you can see it, the absorption phenomenon, and then the fluorescence lower in energy. You can see. Now you can see the absorption, which really happens. It can go from S0 to S2 or S0 to S1, and relaxation always happens from the first excited, the ground state, that is your S1 to S0. You also have the relaxation possible from a ground state, that is your triplet to the singlet ground state. So you have phosphorescence. So this picture gives you the absorption, fluorescence, phosphorescence, connecting energy positions. Basically that was giving in terms of time and time representation. Here it is really modified to give the energy position of all these spectral observations of the absorption, fluorescence, and phosphorescence. This is the diagram. One can use it to represent the absorption, fluorescence, and the phosphorescence. Right, what really happens when you go for the excitation, absorption of photon, you can see it, absorption really puts the molecule, absorption happens in femtoseconds, and that really excites the electron to the upper stage, electronic state, and finally it relaxes to the S1 state. From S1, it comes to the ground state in terms of radiation, is the fluorescence that you normally see it, and that is your fluorescence observation in the nanosecond time scale. You also have the non-radiative relaxation. It's a kind of a simulation I have given it so that you feel it what actually happens inside the molecule. I request all of you to mute your audio so I hear some sound from your side also. So now, what are these states that we talked about? It singlet, triplet states. Now, if it is a singlet state, it's called as a singly degenerate. Triplet state is basically a triple degeneracy. It talks about the electron orientations and alpha and beta spin of the electron. If you have an alpha beta combination, it's called as a spin singlet. You can see the first arrow talking about this spin singlet. You have triplet states, you have an alpha 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 beta 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 combinations. You also see an alpha beta in singlet state and alpha beta in triplet state. There's opposite direction, but you see the phase is different. In the case of singlet state, it is opposite direction and out of phase. Whereas in the case of triplet state, alpha beta is out of opposite directions in phase. That is how these are the states that we are dealing with, singlet state and the triplet state. So this gives you a basics of understanding what exactly we mean as a singlet state. electron positions in the ground state and the excited state and orientation of the electron. They're all given clearly about the state representation, right? So after learning all these basics of the absorption and relaxation phenomenon, you also have a question, why should I use fluorescence? Mostly you may see that, oh, it's pretty, fine. But the pretty is not enough. You have a lot of extraction of information. That's very important. It provides information on the molecular environment. And more important is very, very sensitive also. It can give an information about ions, electric fields, viscosity, polarity, pH, temperature, and so on. So all this information can be extracted when you study the fluorescence, and this is very, very important. Now, fluorescence, as I told you, it's very, very sensitive. You can go up to the sensitivity of the sub-nanomolar, or even you can measure it in a femtomolar volumes, and then you can study about the single molecular spectroscopy also. This is all possible with the fluorescence spectroscopy. That's the reason why fluorescence has become a domain of all disciplines, physicists, chemists, and biologists. You can see a lot of applications in biology. This is an important technique, and that's the reason why you can adopt to understand further. Fine. So as we now see the basics, now we should also have the history. History always tells you about how exactly people really gone through all these hurdles. Exactly, you can look at what has happened over a period of time. This is an important thing. Now, the Charles in 1574, is basically a first early contribution that came from materials, how exactly fluorescence was observed. But at that time, it was not known as a fluorescent, but still they have identified some light emitting compound. That's how it went on. And then 1577, and there's another Spanish physician, botanist, and on the medicines of the New World, from a Mexican tree that he was trying to look at it, Robert Boyle, and he was basically looking at the essential salt and addition of an acid, abolished color of the substance. That is very important contribution. And Galileo described also emission of light is basically a phosphorescence. You always see it in 1612. Brewster is important contribution, and which was occurring, fluorescence occurring from a chlorophyll was the one he was representing or discovered it, and it is in the year of 1833. Herschel contribution is becoming a very foundation contribution for the fluorescence is concerned. And the nomenclature was later on given by Stokes, as we all see that. Stokes is very important. And in fact, his paper that published in the year of 1852, it almost runs through 100 pages. He initially called it as on the change of refrangibility of light. He not even named it as a fluorescence, but later on it was called as a fluorescence. That has mostly accepted it. This is how you can see the history of the contribution towards the fluorescence. And that is how he has done the experiment, which I already picturized it in a simple animation. So you can see the different selection of wavelength and then detection. This is very important. Now, if you look at the summary of the early discoveries, that is how I listed it. You can see the overall list of I don't want to read out because of shortage of time that we have it. You can put it in the recording, and also I'll share the PowerPoints. The whole history is given. And also 20th century, there are a lot of milestone contributions. So mirror symmetry relationship is one important contribution. And then the Perrin law, Kasha's law, and all of them are very important. Polarization of the fluorescence, they're all important contributions. So you can see the entire contributions in the 20th century is also forming history for the fluorescence is concerned. Right. So now here comes is your nomenclature. Many times I see that the people are confusing with the nomenclature, how exactly they are calling it, what nomenclature you can use it. So when there is a light matter interaction, there are many possibilities. You can have the possibility of scattering absorption. Absorption is an important requirement for the luminescence or fluorescence or phosphorescence. So when you have the absorption of light and the light is emitted by the sample, is called the photoluminescence. So the photoluminescence can be fluorescence, phosphorescence, And you also have the other luminescence, electroluminescence, thermoluminescence, chemiluminescence, and bioluminescence, and so on. They're all, overall, it is called as a luminescence. It's a common nomenclature is luminescence. Sometimes, if you are not sure about the spin multiplicity of the excited state, whether it's a singlet state or a triplet state, and you generally call them as a luminescence. That is also happening in many of the coordination compounds. You can see that it is called the luminescence. And if it is coming by absorption of light, you call them as the photoluminescence. If it is from the other phenomenon like absorption of energy by electrical energy or by chemiluminescence and so on, so you have to use the proper nomenclature. That's very important. Sometimes people confuse with this jargon of the luminescence, and sometimes they also have a question, what is the difference between a luminescence and fluorescence? So luminescence is basically an emission of ultraviolet or visible light, and that's how it was represented. Now, if you look at the nomenclature fluorescence, it came from a fluorspar. Fluorescence comes from fluorspar and opal sign. That is how they combine these two words, call them as a fluorescence. Similarly, you can also look at what is phosphorescence is. Phosphorescence is also by a combination of words. So you can see that phosphorescence is a phosphor, basically, which bursts light and phosphor, and that is how you have the photon. First word is the photon, the other is the bearing of light, which is your to bear phosphorescence. So that's how you have a nomenclature coming up for the fluorescence and phosphorescence and luminescence. So try to have a clarity on this nomenclature. This is very, very important. And also you look at the other luminescence phenomenon like a photo, in addition to photoluminescence, so far what we have said, radioluminescence, cathodoluminescence, electroluminescence, thermoluminescence, chemiluminescence, and bioluminescence, triboluminescence, sonoluminescence, and so on. This is how you have a different nomenclature for different, our interest is to understand the light absorption and the luminescence, which is your fluorescence and phosphorescence. So we'll try to understand we'll focus ourselves on the photoluminescence. Let us not go into the other luminescent behavior, right? So when you focus on this, first initially on the fluorescence, and what are the parameters you will come across in the fluorescence emission spectrum, excitation spectrum, quantum mode, polarization, otherwise you call them as anisotropy, and fluorescence light. And these are the 5 parameters we'll be looking at it and try to understand what exactly happens when you try to, as we go into the details of the lecture, right? Now, what is basically a fluorescence spectrum? Again, and as we raise the question, what is an absorption spectrum? Fluorescence spectrum is a plot of an intensity of the light emitted by the sample with reference to the wavelength. And that is what is fluorescence spectrum. How do we record it? Here in a fluorimeter, you will always see it. There are 2 monochromators. So one is for the wavelength, light selection wavelength, that is your excitation monochromator. You have the spectral distribution of intensity of the light. You always measure it at 90 degrees and scan the monochromator of the emission, and that gives you the spectral distribution. That is what you see as a fluorescence spectrum. Now, you look at the fluorescence spectrum, you can really see that you can see within the absorption band. Otherwise, fluorescence spectrum is excitation wavelength independent. Fluorescence spectrum lies longer energy than the absorption spectrum. Fluorescence spectrum is a good approximation. You can say that it's a mirror image relationship between the absorption and the emission. These are the 3 fundamental basics of the fluorescence spectrum. You will see it. And now it is independent of wavelength of excitation. If you have only one absorption, within the absorption band, wherever you excite it, it is independent of excitation. If you have more than one absorption band, even if you excited the different absorption band, you see the emission spectrum remain the same. This is what is important. This was later on evolved as the Kasha's rule. Emission always happens from the first excited singular state. That's very important. That is the reason why it's independent of excitation wavelength. Now, you also said the Stokes shift, absorption and emission. The lower emission is always lower in energy. This was observed by Stokes. So this shift is called as the energy difference between the absorption and the emission is called as the Stokes shift. And this is very important observation. You also have the mirror image. I'm using the same picture again. If you put a mirror here, you always have a mirror image relationship. These are the three basics of the fluorescence you should understand. They are independent of excitation wavelength. You have the what is happening for the second law is the Stokes shift. Second observation is Stokes shifted. The energy of the emission is always lower than the absorption. The third one is you always see a mirror image relationship between the absorption and the emission. These are the 3 points you should understand as long as the fluorescence is concerned. Now, you also have the second parameter, which is your excitation parameter. What is an excitation parameter? Again, it is the plot of intensity versus the wavelength. And what is the wavelength that you are looking at now? In this case, you are going to scan the excitation monochromator. In the earlier case, you have scanned the emission monochromator. Here now we are going to scan the excitation monochromator. As you scan the excitation monochromator, fixing the emission monochromator, you can see that the intensity is varying it. That spectrum is called as an excitation spectrum. Now you can compare the excitation and absorption also. They look similar. You know, this is very important. And generally they are similar. There are sometimes you will see it, they are different, and this is possible when the geometry of the ground state and the excited states are different, and also more than one components are present in the solution. These are all possible when there is a excitation difference. Now, looking at the comparison of the excitation and emission, you can see it. They are mirror image relationship, which I already mentioned it. Now you can compare all the spectrum together: absorbance, absorption spectrum, excitation spectrum, and the emission spectrum. So they look similar. You will see a mirror image relation between the excitation and the emission, and also between the absorption and the emission. This is how you can see it. Energy wise also, excitation and the emission, they all overlap. It's an overlaying of the spectrum that you can see it. So this is how you can compare the absorption, emission, and excitation spectrum. Now if you look at how exactly you record all this, compare it. Now the absorption spectrum is recorded by scanning your monochromator, which is your only one monochromator, which is basically is excitation monochromator. When you go for a fluorimeter, there are two monochromators. Excitation spectrum is recorded, fixing the emission wavelength, and then you are scanning your excitation monochromator. Whereas when you go for absorption, what you are measuring is the intensity of transmitted light in 180 degrees geometry. In the case of the emission, you are measuring at 90 degrees. What you are measuring is the intensity of the light. We will learn more details on the instrumentation part when the next sessions are there. Now, when you look at the emissions, emission spectrum, you are fixing the wavelength in the excitation monochromator, scanning your emission monochromator, measuring the intensity again. This is how the three spectrum: absorption, excitation, emission can be compared, spectrum can be compared, and the recording procedures can be compared very well. This is very, very important to look at it. Now, when you look at the energy gap law, one spelling mistake is there, when you find. Now, when you look at all these, there is a laws governing it, and the energy gap law is very important law. As you see the energy, right, as I made a beginning, energy gap law, the energy gap law tells you about the energy transfer rates, the gap correlation. The gap is larger, relaxation rates are slower. When the gap is smaller, the relaxation rates are faster, and this also forms the basis for the Kasha's rule. Now you can look at this in terms of the electronic states S1 and S0. Also you can compare it. You can compare between the S1 and the triplet states. Also you can compare it. You can also compare in terms of the higher electronic singlet states and S2 to S1. The gap is really governing all the levels of the relaxation, and this is the important law which tells you about the rates of the relaxation, which also forms the basis for Kasha's rule. Kasha's rule telling you about the fluorescence deactivation in organic molecule always happens from the zero vibrational level of the first excited singlet state. But there is an exception for this rule. This is basically an hydrocarbon molecule, which is an azulene molecule. The structure is a fused ring system molecule. You can see that how exactly this molecule really talks about the absorption spectrum, you can see that the S0 to S2 and then S2 to S0, it's a relaxation, that's the emission. Now look at this S0 to S1 absorption of the first excite. This is a little longer energy. That is the reason why this is an interesting molecule to look at it. And this all depends upon the fused ring structure and the electron delocalization that made this molecule to really behave differently when compared to other molecules. But this is the only exception. It is available in the literature for Kasha's rule. And otherwise, in general, relaxation always happens from the zero vibrational level of the first excited state. That is the first principle of relaxation of the excited state, the organic molecule. Fine. And this is again exception, we have seen it. And now we have to look at what are the rate laws, how exactly rate laws are being governed. Now we have to look at the rate laws in terms of their lifetimes, in terms of their quantum fields and so on. We will see one by one. Let's start with the lifetime. And before we go into the lifetime expression, so we'll try to look at the deactivation constants. So radiative constant, that's your fluorescence deactivation. This is your internal conversion, non-radiative. You have an intersystem crossing. And from the triplet state, again, the triplet relaxation in terms of radiative. And this is what we have picturized in the Jablonski also. I'm just redrawing it for your convenience when you want to write the mathematical expression. Now, this is your triplet deactivation radiation, radiative mode. This is basically a phosphorescence. You have a non-radiative. Now, if you have the 5 rate constants given in this, and try to look at what exactly happens to the lifetime. If you look at the total non-radiative deactivation from the singlet state, internal conversion and intersystem, these two are non-radiative deactivation. You have a radiative deactivation happening from the singlet state. Now, if you look at the rate of disappearance of the excited molecule, you can write it like a disappearance of the excited state of molecule A, let us say, which is equivalent to the rate constants of the radiative and non-radiative to the concentration of the excited state molecule. This is a rate law. And based on your kinetic expression, chemical kind that you studied, one can write down the rate law here. Now, if you integrate this expression and then you try to get a correlation, and then you can see the time correlation of 0, what actually happens, and then that can connect your concentration of 0 at the beginning, the 0 concentration, A0, otherwise A1 star 0, and then with time what happens? This is what we have to look at it. Now you can get an expression, at time t, what is the concentration of excited state is related to the A10 e to the power of t by tau n. This is the basic relationship. One can get it by integrating this rate of deactivation of the excited state. Now, looking at this, how do we connect to the lifetime? If you look at this, lifetime of the singlet state is basically given by 1 over the rate constant. So what are the singlet state deactivation? We know that radiative and non-radiative. Sum it up and invert it, that gives you the lifetime of the singlet state. It is not the fluorescence, it is the singlet state lifetime. Now you can also write a similar way from the triplet state deactivation. We have already seen from the deactivation steps. Triplet state can deactivate the radiative mode and non-radiative mode. And sum it up and invert it, that gives you triplet lifetime. So now we have a singlet lifetime and triplet lifetime expressions. Suppose in case from the singlet state there is no non-radiative deactivation, it's only the radiative deactivation, then you can get a radiative lifetime. It's called as a natural lifetime, which is nothing but your tau r, which is 1 over k by r. This is how you get all these 3 lifetimes here. I'm trying to give you the 3 lifetimes. I will bring out all the other things. Now you can look at 3 lifetimes: singlet lifetime, triplet lifetime, and radiative lifetime. This is how you look at the rate law expressions. Can give you an information about your lifetimes of the singular state, lifetimes of the triplet state, and radiating lifetime. And it is also possible to calculate your rate constant, the fluorescence deactivation, mathematically by making use of an absorption spectrum. This is your simply approximate method, but still one can get a rough estimate of your lifetime. This is called the Strickler-Berg expression. So which N basically represents the refractive index, G and G are the degeneracy of the ground and the first excited state. Epsilon is your extinction coefficient. Nu zero is the frequency in terms of the wave number representation. So you can integrate this expression, try to get an information about the K value. That gives you a simple approximate calculation of the rate constants of the fluorescence deactivation. Now, how do we connect now quantum efficiency to rate laws? Fluorescence quantum yield. Basically, what is the quantum yield? It is basically light emitted by the sample divided by light absorbed by the sample. Otherwise, in general, it is output divided by input. That is how you represent the quantum, any efficiency, for example, output divided by input. Here we are referring to fluorescence quantum efficiency. It's light emitted by the sample and normalized or divided by the light absorbed by the sample. That is what is your quantum efficiency. Now again, pulling up this deactivation to make you feel better. As I told you, non-radiative is some of the two deactivations, internal conversion, inter-system crossing. Now, quantum yield, we say that, it can be correlated to the rate constant. So you have the singlet ratio between fluorescence quantum yield if you want to calculate it. You need to understand the deactivation of the radiative. That's the fluorescence deactivation. This is the fluorescence deactivation divided by all the deactivations that you see, which are all competing each other, right? Non-radiative is competing with the radiative. So non-radiative is sum of the internal conversion and inter-system crossing. They're all put together. And also we already said singlet lifetime is equivalent to 1 over KRS plus KNRS. So you can also write as quantum efficiency of the fluorescence is equivalent to radiative rate constant multiplied by your lifetime of the singlet state. That's how you define the quantum efficiency from the rate laws. Now you can also write quantum efficiency of fluorescence. We know that the radiative this constant can be written like a tau r radiative lifetime, as we already mentioned about it. So quantum efficiency can also be written like ratios of the singlet lifetime by the fluorescence radiative lifetime. That is how you look at the quantum efficiency of the fluorescence. Now, same way you can work for the quantum efficiency of the inter-system crossing, quantum efficiency of the phosphorescence. So when you go for the quantum efficiency of the inter-system crossing, you have to consider the triplet state, inter-system formation, and deactivation from the triplet state. So that gives you KIAC multiplied by tau. Yes, that is how you get the quantum efficiency of the inter-system crossing. You can also find out quantum efficiency of the phosphorescence. When you go to phosphorescence, rate of formation of the light is basically your KT radiative, that is your phosphorescence decay constant, multiplied by divided by sum of the two rate constants, radiative and non-radiative, and then multiplied by inter-system crossing, because you should know that what is the efficiency of this state formation. From that it's deactivating. So that is how you can correlate the quantum efficiency of the phosphorescence. So now you have to understand the triplet quantum efficiency here. Triplet quantum efficiency can be estimated from your deactivation and the formation of the triplet state and quantum efficiency of the fluorescence. So you have a quantum efficiency of the fluorescence, quantum efficiency of the phosphorescence, and quantum efficiency of the inter-system. These are all derived from the rate laws of the deactivation. Now you also look at certain rules for the quantum efficiency. You always have a question, can I have the quantum efficiency of the fluorescence more than 1? Quantum efficiency of the excited state can be more than 1. But you just come across somewhere radical reactions having the quantum efficiency larger than 1. If it is a radical reaction, it is possible. But here is an absorption, 1 photon. Absorption gives you 1 molecule in the excited state. It's called the quantum process. So here you can see that the quantum efficiency cannot exceed by number 1. That is the rule called as your Ermilov's rule. So quantum efficiency of the fluorescence from inter-system crossing is approximately equivalent to 1. Otherwise, the quantum efficiency of the whole process that you see, it cannot exceed 1. And then fluorescence quantum efficient, fluorescence quantum field is also independent of wavelength of excitation. As we have seen the Kasha's rule, emission is independent of wavelength of excitation. It's an extension here. It's called the Wavelo's rule because emission is happening from the same excited state. Quantum efficiency also will remain the same wherever you excite it. These are the basic rules of the quantum efficiency. Now you should know the rules of the relaxation, Kasha's rule, and the rules of the quantum field that you have it, and also the gap law, energy gap law, that's governing the rate constants of the deactivation of the excited state. Now you have question, what is your singlet state lifetime? That is also important. When you look at the singlet state, we have already mentioned about it. I'm redrawing it again, re-representing it. See, in a different nodes, you feel like, instead of saying a molecule, I'm saying is a S1. So as we write the deactivation of the excited state, this is already we have done that and recalling it. So S1 at time t is equivalent to S1 at 0 time e to the power of t by tau lifetime, singlet's lifetime. This is what is your excited singlet state lifetime measurements. When you put t is equal to time t is equal to tau 1, what will happen into this expression? If you substitute here tau 1, it will become -1. So S1 subscript t is equal to S0 e to the power of -1. E to the power of -1 is nothing but 1 over e. Now you can see it, the singlet, the concentration is equivalent to S0 by E. This is what is the condition, but that is what is your lifetime. Tau is becoming a singlet lifetime, then that is what you calculate singlet lifetime at the 1 over the E value. That's very important. Otherwise, you can say that the singlet state lifetime, tau 1, is the time taken for the concentration of S1 to decrease to a value of 1 by E of its initial value. It's called as the singlet state lifetime, right? So this is now singlet state lifetime definition. Now we want to look at what actually happens to the fluorescence lifetime. Our focus is always on the fluorescence lifetime, fluorescence parameters. Now look at this. This is to highlight, again and again I'm doing it. Singlet lifetime, when a 1 over E value. So when you calculate from the decay constants, you can 1 over E value. Now you can look at this simulation. Assume I have excited all the molecule to excited state. Now we are going to deactivate the molecules. As it deactivates, the population decreases. Now as I plot the distribution, when you have large, the intensity is related to the population. Intensity of the fluorescence that you are measuring it is proportional to the population. Now all of them are in the excited state. Now we start with the maximum of 1 as the fluorescence intensity. Now we start the time of deactivation. You see there is a depopulation of the excited state. They all emit light, comes to the ground state. Now we have already seen it. When you take a 1 over E value, that will give you the lifetime. Now same thing, you can measure it for fluorescence intensity decay, 1 over E value, that is nothing but your 30% of the initial concentration. When it comes, see that initial intensity, 1 over E value, and that exactly the lifetime of the singlet state. This is the basis of the measurement of the singlet state lifetime. This is what we are going to learn it. When you use the TCS-PC as a technique, how do we measure it? Now we have a lot of computational method. When we were all students, there's no computers. You have to draw a fluorescence intensity decay and then find out 1 over E value. That gives you the lifetime of the fluorescence decay. But now computers help you to do all kinds of a deconvolution and then try to give you the information. But actually, this is the basis of the lifetime calculation, 1 over E value. Now, from the previous view graph, you got an information why it has to be 1 over E value. This is what I have shown you here. Right, now if you can find out the intensity decay with time, you can measure the lifetime. This is the basis. Now the last part that you have to look at is anisotropy. Anisotropy is the one which really talks about the orientation. Anisotropy, when I say it, is the orientation dependent. Now, what kind of a orientation we are talking about is the orientation of the light as a transition, and then also look at the orientation of the transition dipole of the molecule. This is very important. This is to feel you, I've given you all this rotation orientation. Now, when you look at the normal light, it's an unpolarized light. It is coming in all directions. When you look at the linearly polarized, it's basically a plane polarized light. You can have it in one plane. and you can also have partially put. This is how light can be. Now look at the molecular absorptions, how they are polarized. So this is called the polarization absorption. All the electronic transitions. The electronic transition, nothing but the transition dipole moment. So now you look at this, anthracene as an example. You have the first absorption is oriented in the vertical direction. The second absorption is the horizontal direction. Now we are going to give light to the molecule, which is a plain polarized light. This is the polarization, let's say linearly polarized. It's a vertically polarized. Now when the molecule is oriented horizontally, there is not going to be any absorption at all. This is very, very important. We know absorption is a resonance phenomenon when you give an unpolarized light. When you give a polarized light, there is a selection of orientation is also there. That is very, very important requirement to understand the anisotropy. Now when I make the parallel to the excitation polarization, and you see the maximum absorption, and if there is an angle of kind of orientation of the molecule, then there is a cos squared theta relationship. This is how the orientation of the transition dipole to the orientation of the excitation electric dipole always makes you to understand what really happened. There is a selection. This is called as the photo selection rule of the orientation. This can be summarized here. Photo selection rule. Fluorophores absorb photons with electrical vectors parallel to the axis of the transition moment of the fluorophore. This is the basis. So how exactly they are oriented? For example, I take a randomly oriented molecule. In this, all the molecules will not absorb light. Now, when I give a plain polarized light, which are the molecule oriented parallel? The red ones that you see, they're all parallel to the excitation electrical vector, and they all get excited. Rest of them do not undergo excitation. Whereas the story is different if you are giving an unpolarized light. When you give an unpolarized light, all the molecules will absorb. When you give a plain polarized light, this is the story. So now you make use of this photo selection rule. When it is absorbing selectively, when it is emitting, the same polarization will be there. Now, when the molecule is in the excited state, if there is not undergoing any motion, the fluorescence anisotropy orientation will also be the same. The molecule undergo all kinds of rotation. You have motions, and you have random motions, right? Brownian motions. All these motions are there, and they really make this fluorescence orientation of the emission dipole is different, and that is the parameter we are using it. What information you can extract? You can have a ratio, kind of a fluorophore rotations. You can get an information about the size, shape of the molecule. All that is possible. You can use this extensively in biological application. We're going to do a separate session on this anisotropy. I'm giving you the basis here. Anisotropy is basically a photo selection of the molecular absorption by orientation of the electric dipole. This is the interesting behavior of the molecule, how exactly you have an. So when you try to measure these anisotropy, certain parameters you should understand. When you do a anisotropy with a steady state fluorimeter, you call them as a steady state anisotropy. You can also do this anisotropy in a time resolved mode. That becomes a time resolved anisotropy. When I make the light parallel to the z-axis, now you see that z-axis is parallel, and you have two other axes, y and x are perpendicular. Now you can see that x and y are perpendicular. Otherwise, total intensity is equivalent to one along the parallel axis, two along the perpendicular axis. If I change the orientation to the parallel to the x-axis, you have two perpendicular axes. Now, same way, if I make it parallel to the y-axis, you can have the y-axis is parallel, rest of the two are parallel. You can also use the nomenclature vertical and horizontal also. When it is parallel, you call them horizontal. When it is perpendicular, you call them as a vertical. These are the nomenclature they use it when I try to understand the anisotropy of the molecule. Now, how do I generate a polarized light? Plain polarized light is use a unpolarized light, put a polarizer in between, you get a plain polarized light. Normally, these polarizing devices, it can be a sheet polymer based polarizers or a calcite crystal, and these are the two polarizers. They have a different family of polarizers, like a Nicol polarizers, Glan type of polarizer. They call it the Glan-Thomson polarizer, Glan-Taylor polarizers. Basically, it's a birefringent material that is used, and 2 refractive index material. Birefringent is nothing but the 2 refract. They have a 2 refractive index, and that really makes you to have the selection of an unpolarized light to a polarized light. So you put a polarizer in the excitation path, and that gives you a plain polarized light. Now you put a polarizer in the excitation. Now, as we already mentioned, there is going to be a selection of the excitation, right? Same thing if I put it for a polarizer in the emission light, I'm going to measure it. So it is, I can orient the excitation and emission either parallel or perpendicular. I measure the intensity of the fluorescence either in the parallel or in the perpendicular orientation. That is what we call them as a I parallel, I perpendicular. So you can use the 2 parameters. One is called the polarization ratio, which is nothing but the difference in the I parallel to I perpendicular divided to sum of the intensities. And this is what is called as the polarization. Now, if it is parallel, the intensity will be maximum 1. If it is perpendicular, it will be 0. If you take the ratio, maximum intensity number for P can be 1. And if it is, you give in one direction, the molecule is oriented in perpendicular, it can be -1. So the range of value of the polarization can be from +1 to -1. They also another parameter, measuring parameters. Here, if you look at it, they simply use only one perpendicular orientation, whereas another anisotropy parameter is called the emission anisotropy. It's called as the R value. They always use the 2 perpendicular. Whenever you have one axis parallel, there are 2 axes perpendicular, right? So they use the entire intensity like this. Here, when you look at the analogy of polarization, this can vary from +1 to 0.5. That's the difference. Whereas the P can vary from +1 to -1. R can vary from +1. Both of them can be used, but basically, anisotropy is extensively used. You can also relate these two also. R and P can also be related. R is equal to 2 times P by 3 minus P. Now you can have a different values of P and R. You can calculate from this expression. This is how the anisotropy parameter can be extensively used to understand the photophysical behavior. From this, you have a lot of applications coming up, right? So to summarize this, what we have discussed so far, it covers the basis of the absorption and fluorescence parameters like emission spectrum, excitation spectrum, quantum yield, rate loss, and we also looked at the lifetimes and anisotropy, right? This is what is the basics one has to understand to start with before you go into the details of the fundamental details of the fluorescence